Well, hello everybody. In today's chemistry lesson, I'm going to teach you how to write formulas for ionic compounds. This is a multi-part video, and today we'll start with part 1, of course, which are the fairly simple ones. It's important to know that an ionic compound is always made of a positively charged ion combined with a negatively charged ion. The positively charged ion is usually a metal, and the negatively charged ion is usually a non-metal. There are exceptions to these, of course. There are things out there called polyatomic ions, but we'll cover those in the next video, part 2. What's also very important to know is that the specific charges on the ions, whether they be positive 1, positive 2, positive 3, or negative 1, negative 2, or negative 3, those are the things that determine the formulas that these compounds will have. Okay? And so it's important for you to be able to determine the charge of ions, and one of the most important things that's going to help you do that is our good friend, the periodic table of elements. If you have a periodic table of elements of your own, what you should do is you should put some charges above some of the columns on these periodic in this periodic table, because the charges that you write there will tell you the charges of all the atoms in those particular columns or groups. So here we go. So above the first group here, group number 1, which contains hydrogen, lithium, etc., we're going to put a nice big +1. Okay, and what that means is that when these atoms are in an ionic compound, they will have a positive 1 charge. Group 2, which contains beryllium and magnesium and everybody else below it, we'll put a nice big +2, because those are atoms that will form positive 2 ions. Now let's move on over across the pond here, and we'll go to boron, aluminum, and everybody else in group 13, and we'll put a +3. We'll move on over to group 15, which contains nitrogen and phosphorus and arsenic, etc., and we will put a -3. Those are nonmetals. They form negative ions. Above oxygen, sulfur, selenium, members of group 16, we'll put a -2. And then above the last group, the halogens, which contains fluorine, chlorine, and bromine, we'll put a -1. So with these 6 groups that are labeled in the way we have them labeled here, elements that fall under those different groups will have the charges that we have listed above them. Now you might be wondering, hold on there, what about this big whole bunch in the center here? Groups 3 through 12. What happened to them? Don't they get involved in ionic bonding? They are metals. Well, this is true, they are metals, and they do get involved with ionic bonding, but their charges will be determined another way, as you will see in this video. Hey, what about carbon and silicon and some of those guys in there? Well, most of these elements that are nonmetals or metalloids don't really form ions all that often, with a couple of exceptions, tin and lead, and we're going to look at them later on as well. And then, as you probably know, that the noble gases over here in group 18, they don't form ions at all because they're noble gases and they undergo reactions. Okay? So with the periodic table listed or labeled in this way, I think we're ready to proceed. Let me show you now how to turn the name of an ionic compound into its formula. So in other words, what you'll be given is you'll be given the name of an ionic compound, such as aluminum oxide, and your task will be to turn that into a formula. And the process by which you do this is actually fairly reproducible and not all that complicated. I'm going to show you several examples and then give you a chance to practice on your own. With many of the examples, there will be a new twist or a nuance or a new thing that you'll have to remember. But with practice and time, it'll all become second nature. So we'll start by writing a formula for aluminum oxide. How do we do that? Well, first we start by writing a symbol for each of the elements represented here. Aluminum symbol is Al, so we'll just write Al. And then oxide, well, oxide sounds a lot like oxygen, and it is oxygen. So let's give write a nice big O for oxygen. There we go. Step 1. Step 2, let's figure out what the charges on these ions will be. Well, if we go use the periodic table that we have labeled here, we'll go find aluminum. There he is. And he's in the column where the ions are +3 charged. So we'll put a little +3 in the upper right-hand corner of aluminum as a superscript. What about oxygen? There's oxygen. Oxygen comes in the column where they're all -2, so we'll put a -2 right there for oxygen. Wonderful. So now we know the symbols of the ions as well as their charges. Now we're ready to turn this into a formula for real. The technique that you use at this point is what's called the crisscross method, because what you're going to do is you're going to take these two superscripts, these two charges, and you're going to crisscross them. You're going to move them down and diagonally down to become the subscript of the opposite element. So this 2 here will move down here and land itself right there and become a subscript for aluminum. And this 3 will shoot its way down here, crisscrossing with the -2, and become the subscript for the oxygen. And so the resulting formula of aluminum oxide is Al2O3. And there you are. As you can see, this 3 started off as a superscript for aluminum, but ended up as the subscript for oxygen. And this -2 started off as the superscript, or the charge for oxygen, and ended up as the subscript for aluminum. You might be wondering, what about the positive and the negative charges? What happened to those? Well, when you do the crisscross method, you simply get rid of those charge symbols. They are not needed. And here's why. It's because this +3 denotes the charge on this aluminum ion, and this -2 tells us the charge on this oxygen ion. These two numbers here indicate an imbalance between protons and electrons and describe the electrical nature of each of those ions. But when you crisscross them or move them down to become subscripts, they change jobs. This -2 began as the charge on oxygen, but ends up telling you how many aluminum ions are in this compound. And this +3 starts off as the charge on the aluminum ion, but becomes the subscript of 3, telling you that there are 3 oxygens in this compound. So this compound, or one formula unit of it, is made of 2 aluminum ions and 3 oxygen ions, and there's the formula for aluminum oxide, Al2O3. Our next example is the wonderful calcium fluoride, and this one will have a little bit of a twist to it. Let's begin writing the formula for calcium fluoride in the same way as the last one. We'll start by writing the symbols for each of these ions. Calcium symbol is Ca. And fluoride, well, that sounds a lot like fluorine, and it is. So let's write an F for fluorine. And there you go. Now we can consult our good friend the periodic table and find out the charges on these ions. Okay, so calcium is right there. Calcium is in the column where the ions have a +2 charge. So let's do that. Let's give calcium a charge of +2. And fluorine, where are you, fluorine? There you are, top of the halogens. You're coming in at a -1 charge. And there we are. So we have the symbols as well as the charges of the ions. Now we are ready to crisscross, okay? So we'll take this 2, and then we'll come down here and become the subscript for the fluorine. And we'll take this -1, it will come down here and be the subscript for the calcium. And now we've got a nice formula, CaF2. Okay, you might be wondering, hey, wait a second there, Mr. Moffat. What happened to the 1? You didn't write it down there. That is correct. Here's a new little rule or nuance, is that in a formula for a compound, when there is only one atom of an element to be represented, we simply represent it by the symbol itself. Or, in other words, a subscript of 1 is never written. This rule is similar to the rule in algebra. Right? If you were doing algebra, for example, and there was a variable of 3 times x, you would write 3x. Or 4x would simply be written as 4x, 2x, etc. But what about just plain x? Would you write 1x? Would any of your algebra teachers write 1x? No, they would not. They would simply write x. And the x symbol alone implies only one of them. The same holds true for calcium. That implies one calcium ion. Most of you probably knew this already and didn't realize that you knew it because you did know the formula for water, H2O. And if you were asked to interpret that formula, you would say, yes, a water molecule is made of 2 hydrogens and 1 oxygen. Could you imagine what it would be like if somebody wrote this formula? You would tut-tut that poor soul and say, oh, sweetie, what happened? Who told you that that was the formula for water? It's not. Well, that rule of the invisible one, as I like to call it, applies for these ionic compounds and pretty much all compounds. All right, so there you go. There's another example, calcium fluoride. Moving right along, let's look at another one. Aha! Here we go. I like this one. This is beryllium oxide. All right, same technique. Let's write down the symbols for beryllium and for oxygen. Beryllium is Be. And then oxide represents oxygen. That would be our good friend O. Now let's find their charges using our friend the periodic table. Beryllium, where'd you go, beryllium? There you are. You're in the positive 2 column. Oxygen way over here in the negative 2 column. So we'll give beryllium its positive 2 and oxygen its negative 2. Now we can utilize the crisscross method. And we can figure and bring this 2 down here and this 2 down there. And what you end up with is Be2O2. However, in this particular case, you are not done. Here's a special extra rule or new rule for you is this. When you crisscross the subscripts, if they appear to be able to be re-expressed in lowest terms, then you should express them in lowest terms. Or in other words, if they can be reduced in the way that a fraction is reduced, then you should reduce them. Formulas for ionic compounds are always written with subscripts in the lowest whole number ratio. Or in other words, the subscripts are always written in lowest terms. So 2 and 2, imagine if that were a fraction. 2 over 2. 2 over 2 could be reduced to a fraction, or in simpler terms, of 1 over 1. And so that's what we're going to do. We're going to take 2 and 2 and reduce them to 1 over 1. Or 1 and 1, I should say. And since 1s are invisible, the formula for beryllium oxide is BeO. That one right there. So there's a new twist or nuance. If the subscripts can be reduced after crisscrossing them, then you should reduce them. Another way to say this, I suppose, is that if the subscripts match each other, you can just get rid of them and turn them both into invisible ones. Next example. Our good friend iron 3 oxide. Hold on a second here. What is that? Well, that, my friends, is a Roman numeral. And that's the Roman numeral 3. Well, what the heck is it for? Let me explain here. Let's go back to our friend the periodic table. I owed you an explanation for groups 3 through 12. We didn't put any sort of headings or numbers on the tops of those groups. Why? It's because many of these metals, but not all, are what we call multivalent metals. In other words, these are metal ions that can have more than one possible charge. Iron, for example, is a multivalent metal. Iron can form 2 different ions. It can form a positive 2 ion, or it can form a positive 3 ion. Cobalt, nickel, copper, manganese, chromium, gold, titanium, and vanadium are all well known as multivalent metals. This is very different from the other metals that we've looked at so far, like magnesium and calcium and beryllium. Beryllium ions are only positive 2 charged. There's no other possible charge for beryllium ions. Same for magnesium, same for calcium. Potassium can only form positive 1 ions, and aluminum can only form positive 3 ions. The ions in these three, the metals rather, in these 3 groups don't have the option of forming other ion charges. But the guys in the middle, many of them are multivalent and they have multiple possible positive charges. That, my friends, is the job of the Roman numeral. The Roman numeral is tied to or associated with the name of the metal that it comes after. It tells you the charge on that ion. And so we can use that then to write a formula for iron 3 oxide. So what we'll do is we'll write the symbol for iron like we did in the previous examples, and then oxide is oxygen, we'll write a symbol for oxygen. Now, what does iron 3 mean? Iron 3 means iron with a +3 charge. Oxygen, as you might remember, is one of the elements that we can use the periodic table to help us with. Oxygen ions come in at -2, so we'll put in -2. And now this question can proceed like any others. Or not question, this formula writing. The 3 can move down here and become part of the oxygen. The 2 can come down here and be the subscript for the iron. And our symbol for iron 3 oxide is Fe2O3. The formula, I should say. And there you are. One must be very careful. It is very tempting to see iron 3, an element followed by a number, and then to automatically assume that iron gets a subscript of 3. Here, let me put this onto the camera a little bit better. Realize I'm losing space, running out of space here. Here we go. No, ladies and gentlemen, wrong. Oh, okay. The Roman numeral, the job of the Roman numeral is to tell you the charge of the ion, of the metal ion that it comes after. So this 3 right here refers to that right there. Okay, so be very careful with what you do with those Roman numerals. It is nice to have them, though, because you don't have to go to the periodic table to look up the charge of iron 3. The charge of iron 3 is given to you right there. Isn't that wonderful? All right, let's look at one more example here, and then I'll throw you some practice problems that you can try on your own. And here we have manganese 4 sulfide. That's right, IV is 4 in Roman numerals. Before I continue, I should say this. If you're not keen on the Roman numerals and you don't remember them too well, then you should take a few minutes out and look them up. The good news is this, is that for these ionic compounds, the highest Roman numeral value you'll see is 7. So if you can learn and remember the Roman numerals for 1, 2, 3, 4, 5, 6, and 7, you'll be all set. You don't need to go up into the 20s and the 50s and the 100s. All right then, let's now write a formula for manganese 4 sulfide. Manganese, let's write a symbol for manganese. It's not Mg. Be careful. It's Mn, manganese. And then sulfide, that sounds like sulfur, and it is sulfur. So let's put an S for sulfur. I'm sorry, that looks a little bit like a 5. My fault. Bad handwriting strikes again. All right then, so what is the charge on manganese 4? Should we find manganese on the periodic table? Well, we could, but that won't help us. Boom, there's the charge of manganese right there. The charge of manganese, +4. And then sulfur, well, maybe we should look that one up on the periodic table. Ah, yep, there's sulfur, comes in at -2. So we'll put a -2 up there for our friend sulfur. And now we shall partake in doing the old crisscross technique. The +4 comes down to become the subscript of the sulfur. The -2 comes down to become the subscript of the manganese. I've been forgetting to mention this, but when you turn these numbers into subscripts, you do want to eliminate get rid of the charge. And so we end up with a formula of Mn2S4. When you write a formula, you should always ask yourself, can I reduce these subscripts? Can I put them into lowest terms? And if the answer is yes, then you should do it. So this actually isn't the correct formula for manganese 4 sulfide. We'll take the 2 and the 4. We'll pretend it's a fraction like a 2/4. 2/4 would reduce to 1/2. And then 1/2 would become 1 and 2, and those become our subscripts. So Mn gets a subscript of 1. Invisible, and then the sulfur gets the subscript of 2, MnS2. That then is the formula for manganese 4 sulfide. Again, the Roman numeral can be tricky. When you see the 4 in the name, you might want to also then see a 4 in the formula, but it doesn't work that way. The 4, again, is the charge of the manganese ion. The charges of the ions don't necessarily show up in the formulas for the compounds that they form. And there's all the examples that I have to show you. What I do have here somewhere is several practice problems that you can try. And here they are. What you could do right now is you could pause the video and then take your time and try these examples on your own, and then hit play again. And when you hit play, you'll see the answers that are here because I'm going to write them. So hit pause now and try these. Alright, I hope you hit pause and then you tried these and now you're back, because now I'm going to give you the answers for all of these formulas here. So nickel 3 sulfide. I'm just going to write them down below here because I didn't leave enough room in here. So nickel 3 sulfide comes out to be Ni2S3, just like so. And then we have our friend gallium nitride, which is a weird one because it doesn't have end up having any visible subscripts, and it just looks like a weird word, GAN. There it is, gallium nitride. Potassium phosphide comes to be K3P. Over here we have copper 2 chloride, CuCl2. Again, be very careful with the Roman numerals. The Roman numeral 2 in the name comes immediately after copper, but the subscript of 2 comes immediately after the chlorine. Be very careful. Then there's magnesium bromide, MgBr2, and then our last friend, barium oxide, BaO. And that's all I have for you folks today. I hope you enjoyed this video. Please email me with any comments or questions. And as always, I say to you all, HAND, which stands for have a nice day.